This talks about the p-n junction and the capacitance that is formed in these junctions. There are two kinds. Number one, with here is the P and the N junction. So we have a P-type material, N-type material, anode and the cathode. And doesn't matter this junction is in a transistor or it is just a diode. Here it is a diode, it just doesn't matter. If the voltage applied to a diode, this is the diode formation. If a voltage is applied in reverse voltage, there is going to be no particular current flowing into the diode. In other words, the current out of the power supply will be practically I as practically equal to 0. There will be a reverse voltage, a reverse current in the diode, known as the reverse saturation current, practically so small. It won't do anything. However, what is going in the diode is the P and an N regions, which is consistent of holes and electrons, abundance of electrons here. When they are interfaced, even with a 0 voltage at the terminal, even if you zero the terminal, part of the electrons migrate from N-type region, N region, and go towards the P region, and they fill the holes. The holes are made from trivalent material known as acceptors, because in a silicon structure, what you need for an atom electrically in order to bond with the remainder of the material is an atom has to have 4 shared electrons with the silicon. Silicon itself automatically has that by itself. All silicon atoms share 4 atoms with the side ones, with their side atoms. But when there is an impurity, you plant it into the material, like a p-type material, it's a trivalent. So it is lacking 1 electron in its orbit. What happens when you make a p-n junction? An electron from the donors, so-called donors of the electron, will be dislodged from the n-type and will go and fill the p-type. And it will create, as a result, a charge in the regions. Because once electron migrates and is absorbed with a hole, the hole itself, in other words, the material itself is neutral. But once it absorbs 1 electron, it will become a negatively charged ion in the region. And it will leave positively charged ions in the N region. So here is the boron. Here is the p-type phosphate. This is the phosphate. Phosphate has 5 electrons, 1, 2, 3, 4, and 5. This one has 3 electrons. Silicon has 4 electrons, Si. Okay. So once this boron is injected into the silicon material, it will be lacking 1 electron in here, missing an electron in here in order to bind with the silicon atom. Because silicons, they form a lattice, a complete lattice all over the place. They all have complete 4 bonding electrons with the neighboring ones. So if there is a phosphorus material here, which has 5 electrons, that electron will go in and will fill this bond. Will fill that bond, so that the boron now will have 4 electrons and it will be able to share it with the neighboring silicon. So once this boron is hidden into the bulk of the host silicon material, then once it accepts an electron, it becomes a negatively charged ion particle, because literally it is a particle which is lodged in the atom. It doesn't move, it stays right there as a negative charge. But what happens to the phosphorus? Because it loses one electron in here, initially it is neutral with a 5 electron, but once it loses one electron, it becomes positively charged. So it leaves positively charged phosphorus atoms in the bottom region. So we have negatively charged ions in the P region and positively charged ions in the bottom region. So this region is called depletion layer because they merge together. It's called the depletion layer. There is no current flow in there, but actually there are current flow in there, but two kinds. One is a positive whole current flow, the other one is an electron flow. They constantly flow against each other and they leave no net current flow in the depletion layer. That's why there will be no net current taken from the power supply source when it is in the reverse direction. Effect of reverse voltage. If this reverse voltage is called VR, and you increase the VR, the depletion layer will start widening. As it widens, it's like aparting the charge, two charges from each other. So that means you have two plates, basically, positive charge, negative charge, this much gap between them. If you start aparting them, widening them, because of increasing voltage, increasing reverse voltage, the capacitance between the two plates will decrease, giving rise to a lesser capacitance. So in a diode, when you apply a negative voltage, we're going to get a capacitance between C and an A. It is known as junction capacitance, reverse junction capacitance, and it will be inversely proportional to the radical of applied voltage. So if you start reversing the voltage and increasing, the capacitance will keep dropping with that profile. This is known as the reverse voltage variable capacitance diode. They call them variable capacitance diode. Special symbol is used. This is the symbol that is used. These diodes are always and always meant to be used in reverse. You will never ever see that diode in a forward region of an application. You want forward current, you use other diodes. You don't use varactor variable capacitance diode. The significance of that is, in the reverse region, you have no current flowing into the diode because it's reversed, and you have a variable capacitance between the two electrodes here, between these two electrodes. The profile that it is changing is shown with this equation. That's the major, known as the junction capacitance. Only works for the reverse situation. So VR is a reverse voltage. Phi J is a junction potential, which applies to the junction potential between these two particular P and N material. With different concentration, you get different junction potential, but the limits of that are between 0.5 to 1 volt for Phi J. The top one, which is known as C0, is known as the zero bias capacitance. What is that? It is the capacitance between anode and the cathode when the applied DC voltage is near zero. In other words, if you take a diode, indeed, it acts like a capacitance for a small signal. Literally, it is a capacitor. You apply, for example, 1 millivolt peak-to-peak sinusoidal, and you will see that the current will be shifted by 90 degrees, just exhibiting impedance of a capacitor. And the value of the capacitance, therefore, will change with this profile. You apply a bias with it, a negative bias, capacitance will get smaller and smaller. What is the range? Typically, manufacturer will give you that information. It's known as the zero bias junction capacitance. So they will tell you what you have here has a zero junction capacitance of 150 picofarad. So you know that, top in the equation. Phi is typically half a volt. Then when you apply a voltage, radical that would determine the how low that capacitance will go, starting say from the 150 picofarad. It can go from 150 down to 2-3 picofarad. So what can you make with it? Right? So what can you make? Let me show you something. This one. Cj 0 is equal to 150 picofarad. This battery is, say, 10 volt. Vb is equal to 10 volt. And is variable, it can be changed. Inductance is L is equal to 1 micro Henry, actually 0.1 micro Henry, can be very, very low, 0.1 micro Henry. Cc, this is 0.1 microfarad, coupling capacitor. Okay, let's see what we have in here. The small signal equivalent circuit of this thing, what do you think it is? You put DC voltages to short. You put very large capacitors, look, 0.1 microfarad. This is only 150 picofarad, right? So you put that one into short. So your DC circuit looks like 100K Cj Cc is a short. This is C of the C coupling. Here is an inductor, L. Don't you have an LCR? See that? LCR. L parallel with a C, parallel with an R, has a resonant frequency. Isn't that right? There's a frequency that if it emits, it can resonate in parallel. The parallel resonant frequency is FR, known as the resonant frequency, is equal to 1 over 2 pi radical LCJ. So we can calculate how much is that. How much is that frequency? According to the values that I gave you, we throw it into the radical. And this becomes the essential part of communication receivers. Every radio is radio, television, anything, cell phone, name it, is working on that principle. They use varactor diodes. So what's the value? Let's put it there. First, we need to know what is Cj with the given information. Check this out. That voltage is 10 volt. There can be no DC current in the capacitor, right? Because it doesn't allow DC current to go there. This diode is reverse because that's the cathode, that's the anode. There is no DC current flowing in the diode either. So whatever that voltage 10 is, the voltage in here is also 10 volt DC. 10 volt average value, okay? So we can say that in that equation, in this equation that we have, C0 is given, phi j, we know it's about half a volt to 1 volt. VR is 10 volt. So we will substitute and try to calculate what will be the junction capacitance. Here, Cj is equal to C0, Cj0, of course, junction 0 capacitance, divided by radical 1 plus VR divided by phi j. Phi j is typically half a volt. So Cj will become equal to 150 picofarad over radical 1 plus VR is equal to 10 volt, 1 plus 20. So Cj is equal to, when we calculate, 21 radical, and then invert, times it by 150, 32.7 picofarad. 32.7 picofarad. Okay. Can we change that capacitance value? Can we alter that? Yes. That's the key. Keep changing this voltage. Take it to a very, very large level. It will get very, very small. But remember one thing, how high you can go. You put large voltage there, this diode goes to reverse, right? Do you remember what happened to the diodes in the reverse region? Boom, breakdown. So the high end, how high you can go, will depend on where the diode breaks down. So it's a limit. 30 volt, 40 volt, 50 volt, they go up to about 40 something volt. So there's a limit how high you can take that voltage in order to reduce the capacitance. The maximum will be where this voltage source is very, very close to 0. Maybe 1 volt. If you go to 1 volt in here, it will be 1 over half. It will be 2 plus 1. Radical 3 is almost like close to 1. So you'll get just under the 150 picofarad. So it will be adjustable from a largest 150 picofarad all the way to a few picofarad, 1 or 2 picofarad. Yes?
Are we saying that the voltage across the resistor is 10 volts? Or are we saying that
there is no voltage across the resistor, it's always 0. There is no current. Because this is 0, okay? No current can be there. No current can be here. This is backward. So all the time, the job of that resistor is to transfer that voltage to diode. In other words, to bias the diode. That's it. What was biasing? Setting a DC voltage somewhere that you want, right? So this is what it is doing. What if I don't put the 100K here? Look, what if you want to make this voltage equal to that voltage, why don't you make it a short? Listen to this. Why we don't make this a short? Okay, if you put this as short, what will happen to the model? Sure, you're short-circuiting your resonant circuit. It will never resonate. See? It will never oscillate or resonate. There will be no voltage on it. So we can't put a short in here. Okay, so we got 32.7 picofarad. Now we will go take it to the top and calculate. So L is equal to 0.1 Henry, microhenry. Therefore, resonant frequency will be equal to, let's see how much it comes to, 0.1 micro exponent minus 6 multiplied by
32.7 exponent minus 12 equal square root that times it by 2 pi. And then invert it. 88 megahertz. That's interesting. This is the center point of an FM radio, 88 megahertz. That's tuning. Can I go to 108 megahertz? What do you think I have to do in here to go to 108 megahertz? Higher than that. A little higher than that.
Lower the inductor.
We've got to, we don't touch the inductor, but we can do it with the capacitor. Let us make the capacitor lower. If you make it lower, lower than the 32, this can go to 108. Agreed? So lower than 10 volt, yes, you can try. Take it to 1 volt, see what will happen. You can get it to that corner or not. And even if you cannot get to that corner that we want, it's possible. Inductor switching. You put another inductor in. So you've got an analog switch in here that brings a second inductor, range. It's called range selector. They go bands, and then tuning within the bands. Tuning within the band is done with the capacitor, with the varactor. Band change is done with the inductor. 4 band. You can go to VHF, UHF, SHF, because they're totally different frequencies. You can do it in one go. You may have to switch different inductor. Absolutely a common practice. This is what is happening in the TVs. Okay, so 88 megahertz is what we got. What will be the lowest end of the frequency we can go? We can make it. Obviously, if you make this voltage near zero, according to that, you will get nearly 150 picofarad over here, 150. So let me calculate for 150, see what will happen. 150 exponent minus 12, okay, times 0.1 exponent minus 6, square root that, times by 2 pi, and then invert it. 41 megahertz. So with VR equal to 0, we get 41 megahertz. With VR equal to 10, we get 88 megahertz. Maybe with a VR off, we have to try how high that is. A larger one, we can get to 108 megahertz. Actually, we can work it out. How much we really need. For 108 megahertz, how much capacitance do I need? Let's work it backward, okay? According to that formula. So I need 108 here. L is 0.1. How much CJ I need? Okay, here's how to do it. 108 mega exponent 6 multiplied by 2 pi times 2. Okay, is equal to that. Square it. Square. Flip it. Here. So I got my LC divided by 0.1 exponent minus 6. Yeah, 21.7 picofarad. That's all I need. Here, I need 21.7 picofarad. 21.7 picofarad. So what is then the voltage you need to produce 21.6 picofarad? I will go in here. 21.7. 1.7, 150, radical, 1 plus, VR we don't know, phi j is half a volt. Solve for VR. So to see how far we have to go, it will be 150 divided by 21.7. We square that, square, plus 1, minus 1, then times 0.5. 23 volt, 23.4 volt, not bad. So if it gets to VR, it gets to 23.4 volt, 23 volt, let's say, 23 volt, we will hit the target 108 megahertz. Exactly. We will be able to therefore scan the easily, even beyond FM radio bands, by changing this voltage here, anywhere from 0 all the way up to 23 volt. Then your resonant circuit will resonate between 88 megahertz all the way to 108 megahertz. That's the radio band, FM radio, 88 to 108. But what is that for? When you resonate. When you resonate this circuit, first of all, notice why I chose 100K and not 100 volt. There is something called Q factor. Q factor is the loss that happens in a resonant circuit. If something has too much loss, it's not going to resonate. For example, if you take a crystal vase, you fill it with water, water absorbs by vibration. It loses the energy. And you try to, make it ring, it won't. Because water is an absorber. It will dampen the oscillation. When it is empty, crystal vase, when it is empty, when you bang it, bing, it goes oscillating for a long time. Now, the longer it oscillates, that phenomenon is called resonance. The longer, the better. So, in order to have a high Q LC circuit, well resonant circuit, you've got to have minimum amount of losses. 100K is typical, it's a very low loss. So what purpose this thing is serving? Okay. If you take one of those poles we were talking about and you put it in here, antenna, you put an antenna there. An antenna at its bottom with respect to the ground, it looks like a Thevenin voltage source with some kind of a resistance, typically 50 ohm resistance that feeds this. This is voltage, is the incoming voltage, the power converted to voltage. It is known as the power available from the antenna. So the flux of power as it comes from a station, once it is intercepted with a quarter wavelength, and antennas have effective area. It is not physical area. It is very close to the physical area if it is a dish. You see, very close to that. But when it gets to the dipole antenna, it's a very small area actually. Very, very small area. So when it gets the power, electromagnetic waves, it excites and generates a current into the LC circuit. And the LC circuit starts to resonate. Resonating exactly to the incoming frequency, which is the radio station, your dialect. All right? And that frequency goes for amplification. So it goes in, amplified a few times until it's a substantial signal. So automatically you can say, if this voltage source happened to be a digital to analog converter, because D to A converters produce analog outputs, isn't that right? So if the D to A is scanning digits up, and the analog is going stage up, you are basically sweeping or scanning the radio spectrum. So once you pick up a signal from a station, you stop at that moment. You stop and you hold your digital and to analog converter at that digital setting, which is a counter that is driving the D2A converter. So it's D to A, there is here a counter. Clock pulse, it generates a code pertaining to that digital number, pertaining to that analog, and that code will be stored somewhere in the memory. Now, if next time you want to go to that station, all you have to do is to call from that memory that code, feed it in, and goes to the D2A converter. Automatically the analog voltage will go to the place where the code was generated for that particular place. And it will stay at the frequency that you want. This is called automatic